wondering if we were taking a big risk or not. So maybe you can kind of take the argument.
Well, you know, since all of the land around present day is rising, the place where you don't want to buy new property is on the current coast of present day.
Okay.
You want to make it one?
Okay. So,
Really, it's one.
Maybe I can comment on Michael Gill's question at the end, which we sort of resolved in discussion at the coffee break, and it was something that I didn't really make as clear as I should that Michael pointed out, and that is when I mix these two impacts on sea level, namely what I call the ancient ice age impact and modern global warming impact. What I'm doing in representing the ice age component of that mixture of forcings is to assume that insofar as the ancient ice age was concerned, that all land ice melting had ceased by about 4,000 years ago. So ancient ice age influence is only continuing to occur because of the memory effect associated with the viscoelastic nature of the system. Right? So there's a separation in time between melting that occurred during the last 100,000 year cycle of ice age occurrence and the modern onset of melting, which most of us believe began, and there's good evidence that it did begin around 1850, around the beginning of the Northern Hemisphere industrialization. So I didn't make that clear, and I think, Michael, that sort of when we got that sorted out, it was a little cleaner.
okay, thank you.
I think you're talking with a lot of interesting general questions about uncertainty assessment.
Yes.
You have lots of sources of information, very different types. How do you assess overall uncertainty? Part of what seems tricky to me is you have this overall constraint that you know how much, at least in recent years, the total change in sea level rise is, and that's not kind of constrains what you do. And how do you think about uncertainty assessment when you have a bunch of phenomena, some of which you may be accounting for, some of which you don't, but you know that the sum is supposed to equal X, and that seems to create a kind of difficult situation in terms of actually doing fair uncertainty assessments. So how do you know that you just haven't had some canceling of errors, and that that the effect is different than what you think, and that you're missing something? I mean, there just seems to be a lot of complications.
One of the additional comment on this is the way in which we can, to I think reasonably high accuracy, separate entirely ancient ice age influence and the parameters of the model that are required to explain it from modern global warming impact. And that is because in terms of the sea level problem, we have a global database. I didn't really talk about that database at all, but we have literally hundreds, in the data set that I've accumulated, I've got something like 500 radiocarbon dated time series from coastlines all over the planet that cover, roughly speaking, the last 7,000 to 10,000 years of Earth history. So the information that we see in that database is clearly information associated with the last ice age, and we use that to fit the viscoelastic parameters of the model. Internal viscosity structure, the elastic parts of the structure to generate the constitutive relation for the viscoelastic model in general, we get from global seismology. So we use basically Lemay parameters that come from seismology for the elastic part of the Green's function. For the viscous part, we use the relaxation of shape, which is encoded in the sea level records to get at the depth dependence of viscosity. And so far as the modern record is concerned, this is occurring on a time scale which is so short that it doesn't interrogate the viscous part of the response at all, and the elastic component of the model parameters, of course, are still fixed by modern seismology. Right? So we're able to achieve an almost complete separation between these two contributions to the net effect, that is ancient ice age influence and modern global warming influence, just because of the nature of the database that we have at our disposal. That's not to say that the solution to this massive inverse problem, right, is not without uncertainty. It certainly does come equipped with uncertainty, and we try to analyze that. In fact, in getting at the viscous structure, we do full Bayesian inversions of all of the data, which can be used to constrain the viscous part of the model. So these are all aspects of the theory that I didn't really try to cover here. I really just tried to focus on this one modern issue, which has to do with the nature of the way in which the sea level record actually encodes this very subtle effect that's associated with rotational feedback. Yes.
So I'm going to try to ask Michael's question in a cruder kind of way.
I'd prefer if you asked it in a kinder way.
You'll get the drift. But I really enjoyed your talk. It's new material to me, and it's just really exciting. But I felt like it was very closed. All of your arguments in terms of supporting your conclusions were all very tight. And to make progress with calibration, with collaboration, we need to know what you're really stuck at, what you can't do. And so I'm still hearing from you, we have all these problems solved. And what I'd like you to do is just say, what are some things that you really worry about and you're really concerned that you really don't know how to do these?
Okay, well, let me go there. I mean, one of the main issues that's involved in the model that I was showing you results from, has to do with the nature of the lack of what I'll call lateral heterogeneity in the viscoelastic structure in the interior of the planet, the solid Earth part of the model. Okay, and when I first started to build the theory to do these kind of analyses, the goal was always to try to find, as global seismology has been so successful in finding, the misfits, the systematic misfits to the travel time data that require for low-frequency seismology, for seismology in general, that there exists important lateral heterogeneity in body wave velocities. So I have been trying to find, using this spherically symmetric theory, the same systematic misfits, the same inability of the spherically symmetric model to fit the totality of the data as was employed in the seismological community to drive all of the advances that have occurred in global seismic tomography. So far, the conclusion in this work is we can't find the systematic misfits that would require us to do this, although we know that there are local places like Iceland, okay, like the Basin and Range Province in the western U.S., high heat flow regimes where there's clearly need for locally very low viscosity quite close to the surface. Right? But in terms of the global record of relative sea level history from coastlines, you have to work really hard to find those places where the spherically symmetric theory fails. So, but I'm still very much bugged about this, right? In terms of because certainly the mantle is in a state of active thermal convection. The creep resistance is thermally activated and therefore is exponentially dependent on the temperature. So what does it mean macroscopically, right, that we fail to find clear evidence for lateral heterogeneity, for example, in the viscoelastic structure on the largest scales? I argue that means that those scales are actually the lateral scales on which there are strong variations in viscosity are basically on the order of the plate thickness, on the order of lithospheric thickness, i.e. scales that are really not, to which the rebound data are just not sensitive. But this is an open question. Why is the model doing as well as it is, using a spherically symmetric structure when we know that that cannot be the truth?
Yes.
There is some evidence from both laboratory data and those seismic polarization studies that the rheology may effect on linear. I'm wondering what's your sense of how important those linear effects are to taking into consideration and we have to worry about.
Yeah, I mean, I didn't talk about this at all. I mean, the model of three-dimensional model of viscoelasticity that I use is a simple Maxwell model. It is a model which physically, if you apply a shear stress to the medium, it immediately reacts elastically and then begins on a time scale that we call the Maxwell time, which for the Earth is about 300 years. It begins to flow like a Newtonian viscous fluid, right? And you know, a lot of the work that has been done in a priori work in deformation studies in the laboratory basically make it very clear that at least in the shallow portion of the Earth, the stress-strain relation is highly nonlinear. The material actually deforms by the climb of dislocations right through the individual polycrystalline grains of which the shallow structure of the Earth is composed. There's still a great deal of discussion as to how deep you have to go before the system begins to look less nonlinear in terms of its rheology. And that is another of these areas in which I ask myself the question, why is it that the model, this simple model, is doing so well when the rheology that is employed in the model is as simple as it is? You know, if the nonlinearity of the rheology were confined to shallow depths, this is, you know, easy to understand why the model is doing as well as it is. But there's a lot of argument out there to the effect that, you know, in the deep structure, the rheology should be nonlinear even in the upper mantle and transition zone, for example. So we look for misfits of the spherically symmetric model to the observations, and again, whether it's in terms of lateral heterogeneity, whether it's in terms of the very low order model we're using for the rheology, it may simply be the case that the data which represent the relaxation of shape that occurs when ice is exchanged between the continents and the oceans is just incapable of actually viewing the important variations in rheology which many believe should also exist. So that's another of these issues which are always in the back of my own mind. Why is it that the model does as good a job as it does?
I'd like to turn to George's talk. And again, I guess both he and I have been away from the Crop Institute for a long time, but I must say that I recognize the stock, you know, just showing the most important aspects of the excitement and so on. But I think that actually you did not cover what I would think is a possibly important area or approach to this issue of uncertainty quantification or systemic risk and so on, and that's networks, dynamics, you know. I mean, you can do so much with large systems of ODEs with, you know, Fokker-Planck or whatever. But you mentioned yourself that there has been a move in the economic literature from the study of control in small ODE systems to sort of agent-based models and so on. And I won't have the time to talk about it this afternoon, but I think that there is a lot to do with dynamics of networks. I mean, there are obvious simple things like, you know, percolation of icing models and so on, but there are much more sophisticated versions of this which are sort of floating around.
Okay, I didn't have time to talk about this also. You're absolutely right that, first of all, the banking system is not a mean field model. The banking system is a random network. Systemic risk problems formulated on random networks. By random networks, I mean a collection of nodes and a collection of vertices, but the number of vertices that issue from the node is itself a random variable, so that the coordination number is random in the network. And the Bank of England, who is doing very imaginative research in this area, has collected data. There's a group in the Bank of England who has generated empirical random networks based on data from the world banking system. And if I was giving my talk to a different audience, I would have shown you these networks, which I can give you the reference. The person who is Andrew Haldane, is the name of the person. He's a chief of risk research in the Bank of England, and it's under his direction that this research was done. And you're absolutely right that it's not an infinite model, it's really a random network. So formulating these questions, systemic failure on random networks, is a fundamental problem. Most of the research on random networks, beginning some 10 years ago, of this type of questions, beginning some 10 years ago by very much cited paper by Steve Strogatz from the applied math community, are empirical. There's very little theory. So if you want to jump into purely numerical simulations and taxonomy of numerical results for interesting models and so on, there's a lot of vast volume of research there. But there is a gap. There's very little we can do mathematically. The kind of things we can do mathematically with random networks is infinitesimal, it's embarrassingly small. And all I can say is that has got to be a priority as we move forward, because random networks are everywhere.
I was curious about that. When you said that you could allow for spatial dependence in your stochastic term.
Yes.
And I'm wondering where in practice you would come up with those data.
That would be for the spatial aspects would be in power networks, because power networks have much more of a lattice system, the interconnectedness. The interconnectedness of a power network is not really a mean field model. There's a local interconnectedness. The thing about the power networks is that we really know everything about them. It's not like it's a random network. We really know the network, and we can do simulations and so on. But there are also reduced models, continuum approximations of these kind of quasi-lattice models. I haven't looked recently into this is like talking from some years back. I haven't looked recently into what the modern research is on systemic risk for power networks. I was looking more at the banking system, and that's where I ran into this. The banks, I was looking to justify a little bit this mean field model in the financial world. And I found that there's a group at Columbia, with Stiglitz being the senior author, who's a well-known macroeconomist. And they are using models that are somewhat just slightly different from the one I'm using. So, if card-carrying macroeconomists with an international profile are using this, why not a mathematician? And that's how I got started into this. It's not that I wasn't aware that the random networks are important.
No, but I'm talking really about more than that. A lot of the literature indeed has to do with trying to fit power distributions to data sets and so on. I'm really talking about dynamics on these networks.
Yeah, I was talking about dynamics too. And you can that's absolutely right. And that's exactly, the static problems are a little bit easier, but dynamics are important. For example, the research on internet traffic and bringing down the internet system today is a failure of this type. Bringing down the internet by some either malicious or some accidental way is a problem of systemic risk. In a random network, I mean, the complexity of the internet, I don't have to tell you how complex it is. It's massively complex. So how do you address that issue there?
Oh, but you can think of fault systems also in this way.
Of what? Fault systems.
Yeah, seismic faults.
Yes.
Just a comment on the network one. The one that's particularly challenging, but the most relevant one is the time-dependent network. That's where everything is false. And that's the one where you can barely get any headway on anything, particularly if you're going to do some sort of stochastic techniques. But I was going to go back to George's large deviation theory. He's often asked a question. So you're essentially minimizing what I would call the least action. You have a least action principle.
It's not quite the least action. But in some particular cases, it does become the least action.
Right.
I think I would prefer to call it a weighted residual because that's really what it is. Yeah.
So can you, if you didn't present enough details of the large deviation theory, do you suppose you know only approximately what the stochastic process is, the noise term? Can you still get large deviation theory estimates, but just simply knowing a few moments of the distribution?
Okay, that's a very good question because it leads into the logical conclusion to this line of questioning is that it would lead you to believe that in order to do large deviations, you have to know every single detail of the problem. In other words, it's a nightmare from the point of view of modeling. And you raise your hands and you say, look, if this is uncertainty quantification, you haven't done anything, because in order to provide this uncertainty, you have to know with absolute certainty all the details of the model to do this residual calculation.
Right.
But the point is, you don't have to do that. It's enough to get bounds. See, the variational problem is a good way to deal with and to say, what if I don't know? What if I don't know the covariance? What are upper bounds that I can get and lower bounds? Lower bounds are a little bit harder to get. But it's like any other calculus or variations problem. The exact solution of it will require details. But if you're satisfied with bounds, like in material science, for example, nobody's asking you the effective properties of materials. Every material is different. But if you look for bounds, they have a certain robustness to them. And so there is a methodology to go into that. And I think it's a good methodology for so-called epistemic or model uncertainty, other than these other uncertainties. If you're not really sure about the model, and you make some relatively simple hypothesis, you say you only know some low moments of the you know the covariance, but you know a few eigenfunctions of the covariance. You don't really know it. Now what? Well, you can get some moments, bounds for it. And I think, and in the end, this will translate into error bars for the R. Okay, the R need not be a number. It could be an interval, which will reflect the uncertainty.
Any other questions or comments? Maybe I was very interested by Joe's drawing relationships between finance and maybe geophysics. So I would like to tell maybe a little personal story about finance and the problems related with modeling. A couple of years ago, the French Academy of Sciences and the French Math Society organized a roundtable just after the crisis to talk about the potential role of mathematicians working in finance in the crisis. Many newspapers in France were saying, hey, all this problem was created by
mathematicians.
By mathematicians, yes. So,
they did say that. But
yes. Okay. So, so one person in the audience said that models were wrong at the very beginning, and it was well known. For instance, Benoit Mandelbrot had mentioned that the data were very far from being Gaussian, and that increased the risk by a huge amount, and so on. And I was very interested by the answer of one of these mathematical finance specialists who said, of course, we knew that the models were wrong, but if we had true models, we couldn't do any mathematics with them. So it was probably better to work out the wrong models and do nothing, and that's why we did it. So it was really a blunt statement.
I hate this answer. I'm really embarrassed that my colleague, is that Nicole Carril who said that?
Well, I didn't want to mention any name, but
well, because she's the one who gets quoted by the newspapers most of the time.
Yeah.
Let me give you what I think the right answer to that issue is.
Yes.
And in the spring of 2006, I decided to teach a course on credit default and the pricing of credit default instruments, credit default swaps. I teach a lot of financial math for the last 10 years. We have a master's program in financial math that I started at Stanford. And I didn't know the subject. I wanted to learn it. So I was maybe a couple of weeks ahead of the students in the class. And there were some very good students. Some of them had worked in Wall Street. And they were really keeping me, I really had to work hard to really to speak the language properly and to keep them interested. And what I discovered within a couple of weeks of the class was that it was a ridiculous subject. The kind of assumptions that they were making were outrageous. It didn't have anything to do with the data. They were using the famous copula, which I think must have come up. Yeah. It's a way when you're dealing with these composite instruments. You know how the subprime mortgage crisis started was the idea that you put together a lot of instruments like mortgages, and then you tranche them according to who's going to get what when there's default. And of course, the idea is that if there are 200 or 300 instruments like that put together, the idea that all of them will fail simultaneously, and the high-ranked tranche, the AAA rated tranche, which is being sold as a separate synthetic bond, that one with default is almost astronomically small. And the way you think of that is that what's the chance that simultaneously 250 mortgages from a diversified sample around the United States would fail simultaneously? It has never happened before. Housing prices in the United States have been rising for the last 180 years. It just never happened. There's no evidence whatsoever. And then, of course, it happened. 6 months before the summer of 2007, in the spring, we have a financial math seminar. There was talk after talk. People would get up from Wall Street, from right and left, and they would calculate the probabilities for default of these instruments with 10 to the minus 3, 10 to the minus 5, 10 to the minus 11. And then in August, it occurred. Okay, so when I saw this, I said to the class, this is absurd. This is an accident waiting to happen. We had an open discussion on this. I criticized it. You might say, well, what was the constructive criticism? What do you propose as an alternative? There are any number of things to propose. They are not so quick. The real answer is that the banks didn't want to spend the money to do the research properly. And they opted for something cheap and quick that had the patina of something scientific. So that they could say, but our research says, and they could sell their bonds. And they did not do correctly the research. They still don't do it. So we were used. We were not the culprit. We were not the guilty party. The mathematics community was used. It's still being used.
Especially since it's not making anywhere like the salaries of the people.
Well, some do make money.
If we were being paid as much as those guys are making, we could.
That's right. Maybe you could look the other way too. Right.
Yes.
Get back to geophysics. The suggestion has been made a couple of times that interacting fault networks are treatable in some of the same mathematical ways. And there is a group of people, I think about a dozen people, who are all taking fault maps for California, breaking them down into small elements on the order of 1,000, a few thousand elements, and calculating the stress interactions. Suppose you slip one of these elements, then you can calculate the stresses imposed on all of the other ones. So it's a highly interactive network. And they're using this to simulate earthquake histories that could occur. And they have a lot of properties that are relatively similar to those of actual earthquake properties. But there are a couple of difficulties they're having. One is they know the model is incomplete. That is, that there are faults that exist and redistribute the stress around the subject area, but they don't know where these are. They know they exist because we keep getting earthquakes in places where there was not a known fault before. And it doesn't matter, I think, for this purpose, whether the faults were there but hidden, or whether they were so small that they would never count but had been enlarged by the earthquakes that happen on them. In any case, those effects redistribute the stress. And another thing is it's very hard to compare the actual earthquakes with these simulated earthquakes because of the fact that the actual earthquakes are very hard to pin on an individual fault. And so it's hard to know what really a metric for comparison. But I'm wondering if some of the mathematical techniques might be useful in taking a stochastic approach to this, to say there are, there's a random distribution of faults out there that we don't know. If we can identify some properties of those faults, then we can look at how that would affect an ensemble of earthquake occurrence. Maybe that's a good topic for some.
It is a good topic. It is a very good topic, and by the way, it is a very direct analog in the financial world. Of course, this is what goes under the rubric of transparency, because most of the time what the banks do is not completely transparent. So when you think you know what the flows of capital between banks is, you don't really know it very well. That's what they tell you. They may not be doing that. So there's a lot of uncertainty in the network that you think you have calibrated what the Bank of England is doing. They're very careful not to go into small-scale things. So there's a very definitely an aspect of uncertainty and lack of information in the network itself, in the design of the network itself.
But there's one important difference. I mean, you know, the faults clearly are near singular interactions.
Yes.
Not mean field.
No, they're not mean field. I took the mean field out. My legitimacy for the mean field is the Stiglitz paper, which appeared a year ago. My legitimacy, namely, if somebody really challenges me, I say, go read that paper.
It's the lamppost.
What?
It's the lamppost.
Well, I mean, I was very skeptical of the mean field model before I did any research with it, and I saw, my goodness, they have no shame. They're doing it.
Okay, any other question or comment? Yes?
So I like very much the ingredients of this approach, the parts of the world that you mentioned, the interaction between the elements, the bounds and the uncertainties, and basically the unknown parts, basically what we don't know about the whole behavior. The difficulty I'm having is what can this approach tell us that we already don't know about system behavior? In other words, what can we learn? What are the predictive properties of this model?
Okay, I think what it can tell you is this, what this kind of simulations, because in the way you formulate the problem, that probably you cannot really do mathematics except intelligent simulations and compiling data in an intelligent way from simulation. What it can tell you is that under certain circumstances, you could be, the parameters are in a regime where everything is stable, but even a small change, a fractional change in one or an isolated parameter of the model can create a very large probability for a systemic failure. This is something that from the input, when you put all this information into the system, you have a network, you have probabilities of the interconnection effects, you put in the uncertainty properly, you put the dynamics properly. At no stage do you expect that there might be a massive failure, as you define it. That the whole system is going to come down when you make a small change. This bulk instability is not visible at the microscopic level. That has to come out of the calculations, and I think that's where the interest from the theoreticians would come.
I think on a general level, most people would agree that indeed this is the system behavior. You start with small perturbation, case of earthquakes, all this constantly growth by small micro-earthquakes, and some of those micro-earthquakes moving around the magnitude 8 or magnitude 9, and there is no way of telling which one will be that system is constantly growth by maybe small perturbations. Some of them will grow and become a system-wide failure. Exactly.
What are you, I mean, what would you like me to do? You want a formula? Is that what you're looking for? I can't give you that.
How these statistical approaches can help us better.
Yeah, I think at the level that we're talking about right now, I think that the quickest way to get into it is through intelligent, structured simulations. And then you hope that you gain enough experience, you isolate simple problems that you can do analytically, and recreate models and paradigms. But I think the starting point would be large simulations which are not very difficult. The simulations of these random networks. You put the information and you calibrate the model to have this threshold behavior. It's a phase transition. You want to model a dynamic phase transition. Phase transition means that you're near a temperature where you make a very small, if you're a molecule in water, you don't know that if you change the bulk kinetic energy of the molecules, you're going to freeze. You're going to change state. The individual molecule has no idea that this is about to happen if you're just a fraction of a degree above the freezing temperature. I think that's interesting in the context, possibly. In matter, I think it's interesting in finance.